Hello, and thanks for using TickBoom. A student has sent through this three-part question, which reads, prove that if for some complex number z, if z plus 1 on z minus 1 equals ki, where k is some real number, then the modulus of z must be equal to 1. Part 2 then asks us to comment on any restrictions in the domain of the locus held by the condition above. And then part 3 asks us to sketch the locus of z. So I think for part 1, we're being asked to prove that if z plus 1 on z minus 1 is equal to ki, then the modulus of z is equal to 1. And I think the best place to start here, which is often a good place to start, is to let z equal x plus iy. That's just a generic complex number. And it's worth noting at this point that the modulus of z, which is what we're concerned with, in this format is equal to x squared plus y squared. So what that means is if we're trying to show that the modulus is equal to 1, then we're trying to show that x squared plus y squared is equal to 1. So let's see if we can get there. So in terms of what we're concerned about, z plus 1 on z minus 1 would be equal to, I just add a plus 1 here, so I'd get x plus 1 plus iy, and here I just do a minus 1, so x minus 1 plus iy. That's how we would write out this fraction in full form. And whenever you're dividing complex numbers, the key is to multiply top and bottom by the conjugate of the denominator, because what that will do is that will effectively get rid of the imaginary part. So we'll go multiply that by top and bottom of x minus 1 minus iy on x minus 1 minus iy. And then we'll just expand and simplify. So on this numerator here, we'll get x plus 1 times x minus 1. And then x plus 1 times negative iy. So that'll be minus x plus 1 iy. And then we'll get plus x minus 1 iy minus I squared y squared. So that's our numerator. And then that's all going to be divided by x minus 1 squared minus x minus 1 iy plus x minus 1 iy minus I squared y squared. Now we can do some simplifying. So x plus 1, x minus 1 is just x squared minus 1. This iy, we will get plus, and I'll just write this first, x minus 1 minus x minus 1 iy. And then negative, well, I squared is negative 1, so negative 1 is plus, so we get plus y squared. In the denominator, the minus x minus 1 iy and the plus x minus 1 iy will just cancel. That's the whole point of multiplying top and bottom by the conjugate. The imaginary part's always going to drop off. And we're left with x minus 1 squared plus y squared. So now simplifying this a bit further, the x and the minus x will cancel. So this will just become x squared plus y squared minus 1 minus 2iy on, I'll just expand this, so we'll get the first one squared minus 2x plus 1 plus y squared. And now what I'll do is I'll expand out this denominator into both the real and imaginary parts. So we'll get x squared plus y squared minus 1 divided by x squared plus y squared minus 2x plus 1. That's the real part of this complex number. And then the imaginary part will be minus 2y on x squared minus x squared plus y squared minus 2x plus 1 times I. And now what we can do is we can line up the imaginary part with this and the real part with this, because this z plus 1 on z minus 1 is, we're told it's equal to ki, which is effectively 0 plus ki. So that means this real part equates to 0, and this imaginary part equates to k. So therefore, x squared plus y squared minus 1 on x squared plus y squared minus 2x plus 1 is equal to 0, and minus 2y on x squared plus y squared minus 2x plus 1, that is equal to k. So if I focus on this bit here, I can multiply up the denominator. We're still left with 0, so we get x squared plus y squared minus 1 is equal to 0. Therefore, x squared plus y squared is equal to 1. Remembering that our modulus is x squared plus y squared, that means our modulus is equal to 1 as required. So that's basically where we get to for part 1. That's how we can show that if this condition is true, then we have a modulus of 1 for our complex number. Part 2, I'll just turn over for part 2. It asks us to comment on restrictions of the locus of z. So basically, I think to think about that, we can look at this other part of the result. So I'll just rewrite that. So we've got minus 2y on x squared plus y squared, x squared plus y squared minus 2x plus 1. That's equal to k. And remembering that x squared plus y squared is equal to 1, we've just shown that, I can insert 1 there. So we'll get minus 2y divided by 1 plus 1 is 2. So 2 minus 2x is equal to k. I can factor out a 2 here. So we get minus 2y on 1 minus x is equal to k, and I can cancel these 2's. And so therefore I can conclude that k is equal to minus y on 1 minus x, or I can just bring this negative down and write it as y on x minus 1. So that's k, that's what k is equal to, and right away I can see there's something there, because that means that x cannot be equal to 1. Otherwise we'll get k being undefined. So that's a condition. That condition kind of can also be thought of as z not being equal to 1 as another condition. And we can kind of see that just from our original requirement. If this requirement is to hold, we can't have an undefined denominator. That means z cannot be equal to 1 either. But what we'll see when we do part 3 is that these are effectively the same condition. Because when x is equal to 1, that's when, if x is equal to 1, y must be 0. That's when z would be exactly equal to 1 anyway. So they're effectively the same condition, but I guess it doesn't hurt to write them both out. For part 3, we're asked to do the locus of this complex number z, to draw it up, to sketch it in the Argand plane. And I think the key to being able to sketch this is to go back to part 1, where we showed that x squared plus y squared is equal to 1. Because remember, if our complex number is z is equal to x plus iy, then z, what it follows in the Argand plane is simply these coordinates, x and y. We're just plotting x and y and seeing what shape we get if we keep picking values for x and y. But if x and y have to follow this rule, x squared plus y squared equals 1, hopefully you recognize this as a circle with radius 1. So we know then that the locus of z will follow a circle. And I'll just sketch that up. So we'll have our real and our imaginary and our origin. Just draw up. We'll have 1, 1, -1, and -1. And so if I just sketch out this circle as best I can, if x squared plus y squared equals 1, z is just going to follow this circle. That's the locus of z. But there's the one exception. At this point here, it's essentially not included. Because when x is equal to 1, or in other words, z is equal to 1, we have undefined conditions. So apart from the point 1, which we're not including, the locus of z follows this circle. And that's that for that question. So hopefully you've been able to follow all that. I think the key really was just thinking, let's define x plus iy, z is equal to x plus iy, knowing that the modulus is x squared plus y squared, and then taking it from there. And I think you kind of get to where you need to get to. For the conditions on the locus, I think this is probably, the most obvious way to think about it. But you probably could have just seen right away, well, z can't be equal to 1 here. We'll just get an undefined condition. And then finally, the locus of z will just follow this circle, which hopefully is quite a familiar result. And something that you just kind of need to get more and more familiar with as you do more questions like this. So hopefully you found that helpful, and tick boom.